Okay, so I believe we are live. Hopefully, I've found the button that says "Go Alive," the green button. So, welcome everyone to our first 2021 webinar. It's a great honor to have Dr. Nicholas Chancellor back to give a presentation on a recent paper that he published. So, Nick is a UK RI Innovation Fellow at Durham University. He specializes in continuous time quantum computing. In fact, Nick Nick helped pioneer the reverse annealing technique, which is currently available on the commercial quantum annealing produced by the D-Wave. Most of you will know the company D-Wave. So it's really a great honor to have him back today to give a talk on a recent paper entitled Performance of Domain Wall Encoding for Quantum Annealing. So without further ado, I will hand over to you, Nick.
Okay, thanks very much. Really glad to be giving another one of these. Thanks for having me. I guess without further ado, I'll sort of go through it. Can everyone see my slides?
Yeah, I can see it.
Cool. Okay. What I'm going to be talking about here is a problem that people often don't necessarily think about, which is how to actually best encode discrete variables into the kind of Ising models that quantum annealers, the best well-known example being D-Wave, but it obviously doesn't only have to be D-Wave, can solve. It also potentially could relate to QAOA type algorithms, which also tend to like to solve these types of problems. As I've already mentioned, the work is based on this paper here that was recently on the archive, but I'll also be giving some background from other papers, and I'll highlight where things come from as I go through it. So to begin, let's think about what people usually do when they map optimization problems where there are multiple mutually exclusive choices and only one option is taken. And this is what are called one-hot constraints. So the example here would be, for instance, a vehicle can only go down one road, a piece of equipment can only be doing one thing at a time. These kind of constraints that kind of come up everywhere in practical optimization problems. So these are relatively easy to enforce, at least conceptually, using quadratic interactions. If this x is a binary sort of 0, 1 variable, for every variable, you just have a sum of these, -1 and squared. And so then this term, you can see it'll be quadratic because it'll only involve pairs of these x's. And it will give you 0 if exactly one of these is 1, and give you something greater than 0 in any other case. So this is sort of conceptually simple, but it requires interactions between all variables. So you'll see why I'm talking about this as I get through to the next slides. But first, let's think about this from a different perspective. So here on the first slide, I was talking about binary variables under a constraint that makes it so that there's only one possibility. A philosophically different way of thinking about it, but that's more or less the same thing, is to think of this as a single variable. And why I'm saying this is a better way to think about it will become clear later on. So this is an idea of, instead of saying I have a variable that corresponds to my truck goes down road A, road B, road C, I have a single variable that can be A, B, or C. And so I can define this now nice 2-index object where I is the value the variable takes, and alpha is the index of, alpha is the value the variable can take, and I is the index of the variable. So this is what people call discrete quadratic models. So they're like They're like QBOs, but the discrete here means that they can be higher than binary. So in general, you could write this as you have a matrix of interactions between two variables and two values they can take. And you have these variables that only depend on what those two are doing. They don't depend on anything else. So if we have this perspective, the one hot encoding I talked about before, you can imagine this in this perspective. In this case, your constraint is now just part of the definition of the variable. And you say, well, anything that violates this constraint is not even, it doesn't make sense. It's a truck's trying to go down two roads at once. This is a quantum computer, but the things it's computing aren't quantum. They can only do one thing at a time. So it's easy to not make this distinction when you're thinking one hot, because each of the qubits does naturally correspond to one value, but that won't necessarily be the case always. So the simplest example is, or the other example commonly seen, I guess, is a binary encoding, where you say every possibility for a discrete variable, instead of mapping as a 1 or 0 of a particular bit, I'm going to map it as a bit string. So say 0, 0, 0 corresponds to truck going down road A, 0, 0, 1 corresponds to road B, 0, 1, 0 road C, 0, 1, 1 road D, etc., etc. But is there another way of encoding other than these one hot and binary encodings? I'll talk about the difference between them and the other thing, which is actually the main subject of this talk, which is these domain wall encodings. So there is actually another nice way to encode variables, encode these discrete variables into either QBO or Ising systems. So a QBO system is a quadratic binary unconstrained optimization problem. It has these variables x that can take 0 or 1. An Ising system, they are also binary variables, but they can take -1 or 1. So you can imagine if you have an Ising spin chain, a chain of products of these variables, and you look at what the lowest energy is. Well, the lowest energy is, because I have this minus sign here, assuming kappa is positive, is for them to all be the same. If I then frustrate the ends so that the ends are forced to be opposite, then the lowest energy state is to have one so-called domain wall where they disagree. Now, if I think about interacting these domain walls together and creating some analog of these nice variables you have in one-hot encodings, what you end up having is, you see, if I take this second one minus this first one, this will be 0 if these two are the same, they'll cancel. But if S alpha -1 is negative, then this will be equal to 1. So it does exactly what I want. It does exactly what the discrete quadratic model is supposed to be. Takes the value 1. If it does this, takes a 0 otherwise. You might ask, well, what if it's going the other direction, where this one's down and this one's up, or this one's minus and this one's plus? Well, it would give you a -1, but that's an invalid configuration. It's the same reason you don't think about one hot when actually sort of two of these variables are 1 or 0 of them are 1. It's, you've broken the constraint and what you have doesn't make any sense anymore. So this is a way of storing information and interacting it. Importantly, you notice this only involves single body terms. So products of these are only going to involve pairs of these. They're going to be quadratic. I'll talk about this later on, that this really encodes this kind of discrete quadratic model, because this product of these two will also be quadratic in these variables, which is good because in these devices, you have pairwise interactions. So think like D-Wave devices. Most other devices too, you'd end up with pairwise interactions. Having an interaction between 3 things or 4 things is difficult. You can use gadgets to make things that act like multi-body interactions out of two-body interactions, but it's difficult and costly. So yeah, you're basically using this to store information. So one thing you notice is kind of cute. If again, I have something like a virtual qubit on the end here and on the end here that I just have constrained. So I replace this with a field term. So basically a term that just penalizes this if it's in the 1 value and penalizes this if it's in the -1 value. Then I can see I actually have 1, 2, 3, 4, 5 places I can put this domain wall, or really what I'm saying is when I've frustrated exactly one of these either fields or couplings, one of these terms, in 4 qubits. So I've already won a little bit over 1 hot because I can have a variable that has 5 potential values in only 4 qubits. Whereas if I wanted to do 1 hot, I'd need 5 and 5. If that was the only advantage to this, it probably wouldn't be that exciting, but there are others, as I'll get to later. So one aside while we think about this is if I have this encoding here, what happens if I say, you know what if I want to do a variable that can only take 2 values? Well, we know a smart way to do that is to just encode it directly into a qubit. That's a bit. Or a qubit, depending if you think of quantum machine. It turns out these constraints on the end, these fields will cancel if you do that. And so it just gives you the normal binary qubit encoding. So this is nice. Basically, these sort of extra field interactions on the end sort of go away, cancel each other, and you recover the normal binary variables. You can actually use this to very naturally make mixed discrete binary problems, meaning we have problems where some variables are binary and some are higher than binary. It works nicely, this domain wall encoding. If you want to know the details on this, there's a paper that describes the exact details of it. I haven't cited it yet, but I'll flag up that citation later on. But the point is this works for mapping discrete quadratic models. It might take a little bit of thinking on exactly how to make it work, but and importantly, you can do arbitrary discrete quadratic models. So, like I said before, since this term is linear, these terms are quadratic. What I mean there is, since this term only involves single values, s's by themselves, this involves at most pairs of s's, single s's and pairs, which are the kinds of things you can make out of superconducting qubit hardware. And generally, it's the kind of thing you'd get out of sort of a Rydberg hardware or an atomic hardware or something too. But you can also do some degree of freedom counting arguments and say, how many possible couplings and single body terms do I have if I'm interacting 2 variables here? And how many different possible interaction terms do I have in this D if I'm just looking at 2 of these in this discrete quadratic model? And I'm not going to do it here, but you count it up and you find that there's no way to have arbitrary interactions that are quadratic with anything smaller than this domain wall encoding. It's sort of optimal in the sense, it's the best you can do, at least in terms of that count. You also have less connectivity. I already highlighted that before, but it turns out that it seems to be important. So now let's think if we implement this. So I've talked about this binary encoding where you just encode everything in bit strings. In principle, that's the most efficient thing you can do, right? You have m qubits, you can, or if you have log base 2 of m qubits, technically the ceiling of that, you can store a variable of size m. So with 3 qubits, you could store 8 possible values, et cetera, et cetera. And then in general, if it's already a binary number, you don't need to constrain some off. Otherwise, you might have to do something complicated. The problem here is, though, if you start thinking about interacting these, and you think about, what if I want to do arbitrary interactions? What if I want to do something where this truck going on this road and this truck going on this road does something bad, let's say. Well, it turns out to extract those, you'll need these big multi-body terms that say this qubit's doing this, while this one's 1, while this one's 0, while this one's also 1, and this grows to be 2 to the size of your different 2 times the size of your different variables. So these multi-body interactions are hard to engineer, and in general, if you want to do them, you need to use sort of auxiliary qubits, extra qubits, to do that. So we won't think about this too much anymore. I just want to flag it up as another option of things you can do. In gate model settings, it's a bit different because you have different kinds of interactions. Maybe these make more sense in some gate model settings. It really depends on the gate model setting too. I think these do have a place in gate model settings as well. So if I look here, I have complete connectivity in one hot, the domain wall linear connectivity, meaning just one after the other. For 2 variable interactions, in either case, you only need to be able to interact pairs of the variable that are making either the chain or the fully connected graph for 1 hot. You don't need to interact more. That's good. That's the thing that really makes these better than binary encodings, which don't get used a lot in quantum annealing precisely for this reason. And this DE, this is edge distance. This is how many edges do you need to hop to get from one qubit to another. And you actually want this to be, if you're thinking of embedding this, so minor embedding it. What I mean by minor embedding it is if you have hardware that has a graph that's not fully connected or doesn't have the connectivity you need to chain together multiple qubits to effectively get a graph that can fit your problem. And so in general, if something's more spread out, it might be easier to put on this hardware. So the problem is, for 1 hot, everything has to talk to everything. It'll be harder to minor embed, I claim, and the evidence later on shows that, than the domain wall, where potentially you can have a layered structure where one end of your chain doesn't need to talk to what's going on at the other end. You actually don't need that much interaction. And this edge distance is just a way to measure this. Let's think of an example here. Let's think of coloring problems. So coloring problem is, I have a graph, I want to color it. And I want to color it in a way, so here I'm thinking maximum coloring. So what I want to do is I want to color this in a way that the same color touches as few times as possible. So as few times as possible could be 0, but it could be greater than 0, depending on the graph. So one example of this is the famous map coloring problem, where any map you can color with 4 colors. A map just corresponds to a planar graph, but you may not be able to with 3 colors. It depends on the details of the map, and it's actually a hard problem to decide if a map's colorable. So here's, if I have a 4 coloring problem on this sort of graph here, where I have a square and then one diagonal, what I see, the 1 hot encoding, everything looks kind of messy and stuck together. The domain wall encoding, I'm already seeing a kind of layered structure, right? So this is a 4 coloring problem on this simple graph. These 2 layers talk to each other, but doesn't talk to this layer up top. And these 2 talk to each other, but not this one. So what I'm going to use for the rest of the problem, or the rest of the discussion here, is 3 and K coloring examples. So 3 coloring, I have only 3 colors. And then K coloring, where I just use twice as many nodes as colors. Both of them I use random edges. So the details of this are explained in this paper here, this Quantum Science and Technology paper. Sorry. Somehow I got to the very end. This Quantum Science and Technology paper. And this paper is also probably the first place to look if you want a reference on exactly how to do this domain wall encoding. Because I've probably gone a little too fast through this. I just wanted to give the flavor, not necessarily get it to the point where you could actually implement it just based on what I said. Maybe if someone's sort of very fast at stuff, they could figure it out, but I would expect you probably need to go look at this paper if you want to actually implement it. I'll talk about how there's actually software that can implement this for you, but I'll explain that later on. So the first thing we want to do is compare these two. Remember, that's what I was talking about here, is how do they stack up against each other. Well, let's actually do a comparison. And let's do a comparison with minor embedding. So this is with, you have your hardware graph. So this is a, say, superconducting device like D-Wave. I actually use the graph of the D-Wave device for this, and this embedding software is made by D-Wave. And what you have is you have to chain these variables together, and basically you constrain some variables to all be the same. And then by interacting those, you can get interactions that you didn't have in your original graph effectively. So if I then look at doing this with this very nice automatic software, well, if I take a 3-coloring problem, so the red and blue are Chimera and Pegasus. These are just two different, the Chimera is the older graph of the D-Wave device, Pegasus is the newer graph. If I do a 3-coloring problem, these embedding ratios are the ratios of how many physical qubits you need per each variable. And this increases as I increase my problem size, which is what's here, which is what you sort of get going down this axis. And I can ask, is this better for domain wall? Or is this better for domain wall, which is this one, or one hot, which is this one? And so up in this quadrant's what I want to see, down here, not so much. However, the thing to remember is this doesn't take into account that each domain wall encoding uses one fewer qubit. So here, for 3-coloring, I see it's doing slightly worse. Actually, the domain wall encoding is doing slightly worse, but that's okay, because for these logical variables, I only have 2/3 as many. It takes 3 to encode one of these 3-coloring variables, one of these nodes in one hot. It only takes 2 in domain wall. So I'm still winning because this guide to the line I is if they were the same. I'm only doing a little worse. What happens if I go to K-coloring? What happens if I have more colors up to either 9 or 12? Well, first off, you see it embeds better if you have the more connected graph. That shouldn't shock anyone. But the other thing you see is you see that the Pegasus, the domain wall encoding, this embedding ratio is much lower for the domain wall encoding. You're doing substantially better for both kinds of graphs. And how much better you're getting seems to improve as you have more colors. This is this layered structure I'm talking about coming into effect. These bottom 2 graphs, this is just an artificial scheduling problem where, again, domain wall does a lot better. And D is just sort of some comparison that isn't really important for what we're discussing here. Let's see what the effect of this is. Let's actually think of embedding these onto a device. So let's say I have a D-Wave chip. Again, this is from this Quantum Science Technology paper. This isn't reporting any experiments yet. I will talk about some of the experiments I've run, but not yet. So let's just look at what size of problem can I embed on some device. This colored shaded area is the range of different values I see for different size of problem. So here, size of graph or number of colors. This is 3-color, K-color. And what I can see here is I pretty much always, well, I do always need a bigger graph for the for doing one hot encoding. So the red is one hot, the blue is domain wall encoding, and you see I can get away with a smaller graph. Well, on this Pegasus, sometimes at the same size, but more or less, I can get away with a smaller graph always using this better encoding. And again, the difference seems to grow with the number of colors for these K coloring problems. So, and again, as I said before, having the fewer variables makes up for the slightly worse embedding ratio. Again, details can be found in this paper, but the point is you can fit it more efficiently onto the device. So this has all been fairly nice so far. I've shown that I can embed more efficiently, but how does this translate to performance gain on actual quantum annealers? And that's something that's hard to answer theoretically. How does this actually affect the dynamics? These are actual superconducting circuits that are going to be doing things. There's going to be bit flips. There's going to be all kinds of entanglement interactions, all kinds of stuff. It could be, it's not what I find, but it could be that the dynamics actually isn't very good at solving the problem on these domain walls, and the fact I can embed more efficiently doesn't make up for that. So some of the arguments you could have is, well, okay, these domain walls, if I think of having this chain, if I flip a variable, I flip from a valid state to another valid state. So it's non-perturbative in a sense. And that isn't true for the one-hot encoding. For the one-hot encoding, if I have one variable that's a 1, and I'm doing a single bit flip update, which is what these devices do, I either have to flip it so I'm in the 0-hot configuration or in the 2-hot configuration and then go back. So that would be a mark in the favor of domain wall. On the other hand, in this domain wall encoding, you have a defined order the domain wall travels in, whereas for one hot, there's not necessarily that structure. There's a more complicated one where these sort of perturbative interactions form a more connected graph through the space. It's not actually a fully connected graph. It's what's called a Johnson graph. But anyway, thinking about this just theoretically is kind of complicated. So what do? We test it experimentally. And this is the recent paper that's the main focus of this talk that I'll talk about. I think before I do, though, I'll check if there are any questions. I actually had this on full screen, so I'll just check. I don't see any. So let me go back to actually talking about the experimental results. Yeah, go forward. If we look experimentally, again, I'm just going to use these K coloring and 3 coloring problems because they're nice and they're good sort of simple test. And if I look at this C, so the C is the number of places the same color touches. So these problems I've designed aren't colorable. There's no way of having no color touch a copy of itself, touch a node of the same color, at least in general. Maybe some of these small sizes are, but in general, I'm intentionally not using colorable graphs. And so then I just normalize by the number of possible edges there are, just so the graph doesn't sort of explode. And I look at different techniques, or look at different the different results. So I look at the 2 encodings, the 1 hot and domain wall. and Advantage in 2000Q. So Advantage is a more advanced D-Wave device. It has this more connected graph, this Pegasus graph. And 2000Q is an older D-Wave device with chimera connectivity, this chimera graph. So if I look at this, and I see, okay, it actually looks to me like, first off, the domain wall is doing substantially better. Lower values are better in both cases. So this is K coloring, this is 3 coloring. And if I look at it, it really looks like actually I'm doing better with this smarter encoding, with this domain wall encoding, even using the older processor. I'm getting a more optimal solution. And you might say, oh, well, that's not within error bars. These error bars are actually standard error, are actually standard deviation, not standard error. Since usually these involve 100 instances, the error bars would actually, the true standard error bars would be 1/10 these size. If you did 95%, it would be 1/50 size, but still they'd actually be outside of them. So let's do some more comparisons to really validate this, because this is quite a bold claim I'm making here, that using a better encoding on the older hardware actually does better than using the less optimal encoding on the newer hardware. Well, let's look at this for 3 coloring. I've just made a nice table here. With this table, I have, on this column is the number this one performs better. So DW is domain wall. 2000Q versus Advantage is a processor. So this column at the end is basically comparing the domain wall and the 2000Q. 2000Q is the old processor versus 1 hot, so the old encoding, on Advantage, the newer processor. And then I can just compare and say which one does better. If they do the same, I get all zeros, which is happening in this 5-node case. They're just all solving it. So that's why there's no comparison there. And I can, why not, calculate the statistical significance, which is basically, can you get a result at least that favorable randomly? What's the probability of that? And then I just conventionally say anything above 95% confidence, or anything with this being below 0.5 or 0.05 is statistically significant. So these are all statistically significant. Here, 40 cases, I've done better with this encoding on the old processor. I never actually saw the worse encoding on the new processor do better. And it kind of just keeps going on like that. You get more and more here. These fails are just where I can't embed anymore. There's a limited number of qubits on these devices. As these problems get bigger and bigger and I try to do this minor embedding, sometimes it just doesn't work. So I just have the software try it. Sometimes it works, sometimes it doesn't. When it doesn't, I put fail. And you can see there's no real surprises anywhere else. Domain wall does better than 1 hot. The more advanced Advantage processor does better than the 2000Q, although it's not always statistically significant. Maybe there's a few cases where it did worse, but they're not statistically significant cases. And so generally you get what you expect. And yeah, so that's shows that this encoding is a good idea and can actually make a bigger difference than a re-engineered processor on solution quality. I can do the same for K-color. I won't spend too much time on this. You get the same basic idea. In this comparison of the 2 processors for 1 hot, you see something slightly weird where the older processor seems to do better. This goes away if I change the decoding strategy. So basically, when I have this minor embedding, I have these constraints that make qubits all be the same. I'll take the same value. There's a question of what do you do if they don't all take the same value? Well, in this case, I've been doing majority vote. If you instead just throw those away, then this goes back to what you expect. This goes back to the advantage doing better than 2000Q. This is just some artifact of the decoding. I don't care about it that much. Otherwise, everything's what I expect, again, for this K coloring problem. Okay. One more discussion about finding the optimal value before we get a bit further into this experimental results and start thinking about why. Well, so this is basically as you expect. There's maybe a small difference from the processor, and there's a huge difference from the encoding, right? So you can see here the two domain wall ones, your probability of finding the answer is much bigger. Okay, first off, also for all this size, the smallest size, either this 5-qubit 3 coloring or this 3 coloring 6 node problem, I'm always solving it all the time in every processor, whatever. But when I'm not, what you can see is, yeah, the domain wall does a lot better. The advantage does a little better, but the encoding, again, is making a big difference in probability to find the answer. One thing I'm just going to highlight about these results is these were only using 100 reads, and I wasn't using any fancy tricks. So don't look at these and go, oh, well, this 3 coloring problem at 15 nodes, the D-Wave just can barely solve any of them at all. Well, no, if I took more samples, this would go up. And if I use some smarter tricks, which I won't go into what all of them all are, I discuss what they could be in the paper, you could make this go up. So this isn't meant to be a measure of the limitation of how well these devices can perform. It's just meant to be a comparison. And I'll compare them, I'm just comparing them on equal footing. And yeah, as I said before, these all solving at lower sizes explain why you get no winner in the first row of these two graphs. Anyway, so let's think about why. Deeper dive into performance, into what's going on. Why are these doing better? Well, let's think about how things can go wrong. Let's think about how you can get a bad answer. Well, one way is encoding failures, right? So what do I mean by this? What I mean by this is if I have this one hot constraint, I've constrained that exactly 1 qubit takes the 1 value, or 1 variable in this constraint takes the 1 value. Well, if either 2 or 0 or any number other than 1 takes that, then what I have isn't really a meaningful solution to my problem. I'm trying to color in 2 colors, let's say. I'm trying to say this is both red and green. Oh, no, it's either red or green. You can't color 2 colors at the same time, at least not in the way we formulated this. What we see here is the one hot encoding seems to be a lot more fragile. It seems to really, as your graph size increases, I haven't talked about how I've set the parameters. You can look in the paper for how I do that. I do this in kind of a sensible heuristic that is fairly common. But anyway, these encodings break down quite quickly for the one hot, but the domain wall, especially for this 3 coloring, they almost always, the constraints are satisfied. If you think about this, for the domain wall 3 coloring, it's actually just 2 qubits, and there's only 1 wrong configuration. So maybe it's not so surprising that you're not finding it very much. For the domain wall, it does eventually break down with a higher number of colors, but much slower than the one hot encoding does. So that's one kind of way you can sort of fail to get a good solution. What else can happen? Well, another thing that can happen is before you're even doing this, you have these minor embedding chains. What they are is physical qubits on the device that you've chained together to make a logical variable. And so you've constrained them to all be the same. And again, the constraint strength I've used is explained in the paper. It's a fairly sort of sensible heuristic. Actually, no, sorry. For these, I've used something called the uniform torque compensation, which is a tool that D-Wave's made that I also verified works pretty well. So here again, you say, okay, what fraction have no broken minor embedding chains? So this is, you have these chains together, and sometimes the qubits disagree because I've tried to constrain them to be the same, but the constraint doesn't always work. Well, what do I find? Well, here I find that domain wall advantage does the best in both cases. But what I've actually see here is these lines for the more advanced processor are higher. So our chain is the rate of unbroken ones than the ones with the less advanced processor. So while domain wall encoding helps, in this case, the more connected graph seems to make a bigger difference. That kind of makes sense because you'll need to chain fewer of these together to constrain to build these variables if you've already got a pretty connected graph. And this is done by automatic software, the same automatic software I was reporting on earlier. The embedding is more efficient also for domain walls, so you do see the domain wall doing better. No real surprises here. But the interesting thing is there doesn't appear to be a trade-off with this domain wall in the sense that it's not like, okay, if I use the domain wall, I can embed bigger problems, but I get more chain breaks, or the constraints tend to be violated more, but I find a more optimal solution. It's every metric I can think of to look at here, the domain wall is doing better. In some cases, it's making a bigger difference than a more advanced hardware graph. In some cases, the more advanced hardware graphs making a bigger difference. If I look at overall solution quality, they all add up to the encoding making a bigger difference. But basically, there's no observed downside from these experiments for encoding the variables in this domain wall encoding rather than one hot. So there's not, at least we haven't seen a way in which one hot is better in these experiments. And actually, in any experiments I've tried, even ones that aren't reported here, we never really see one hot doing better. There doesn't, yeah. So I think actually, again, I'll go check if there's questions real quick. I don't see any, because next I'm gonna. Sorry, go ahead.
No. I said there wasn't any.
Oh, okay.
I saw you were to the code anyway, so I was going to ask about the accompanying code and assets that I saw come with the paper. I think you're going to share it next.
Yeah. So that's where I'm going next. I just figured this was a natural break point rather than having to come back to this. I will have questions at the end too if people have some. Yep. So yeah, that's the next place I'm going. Let me get yeah. So let's say you're running experiments on actually let's go back into presentation mode. Let's say you're actually running experiments on a quantum annealer or really a gate model machine, either way. But let's say you're running optimization experiments on sort of Ising or Cubo type problems. Well, actually, this translated into Ising. So if you're doing Ising problems, which can be translated into these quadratic unconstrained binary Cubo problems, there's some code that's freely publicly available from Durham. It has a DOI. It's also just cited in the paper. The quantum science and technology paper I cited earlier, it's cited there, so that might be the easiest way to find the link. But I'll go through just how you might try this yourself.
Yeah,
so,
I pasted the link on the chat, so thanks.
Yes. You already put it in the chat? I can put it in the chat if you want.
No, I already done that. So
you already did it. Okay, cool. Thanks a lot. Yeah. So, yeah, this is there. You can just try it. Inside of this code, written in Python, there's what I've called the easy domain wall module, and it has a function that I've creatively named make domain wall encoding, which creates these encodings of a discrete problem. And I also made a Jupyter notebook with some simple examples. I'll just quickly go through how this works. It has 3 inputs. One's variable size, which is just the list of sizes of all variables. So if it's 3 coloring, let's say I'm trying to color a graph with 5 nodes and 3 colors, then I'd have 3, 3, 3, 3, have 5 threes separated by commas. And I'm going to call the sum of these sizes R, just because that ends up being the size of other things. Then I have penalties. So these are the terms which penalize different values of individual variables in a 1D array or list. So you could make these all zeros and just encode everything in interactions, but this basically allows you to say, okay, I want to penalize, say, if I'm doing the coloring, I want painting this one green to cost a bit, cost some energy. Okay, you could do that using this. And then interactions are the interactions between variables in sort of an upper triangular R by R array. So that interactions is basically, if I go to this way I've defined a DQM way back here, basically this matrix here, only I've sort of linearized it so that I have IJ on the the vertical and horizontal axis, but then I have the first alpha with I, and then the next alpha, and then the next one, and the next one. And so this total size is again this R, and there'll be interactions within the same variable which aren't allowed. And so this thing is upper triangular, and allows you to define a problem. If you're doing a coloring problem, it will be there'll be sort of ones where you're trying to make 2 of the same color, because it's basically saying, no, don't color those the same color. The outputs, I have what I've called J core and H core, which are the terms for enforcing the domain wall constraints, and J prob and H prob, which are the parts that aren't the constraints. J and H are just field and coupling terms. So this is a matrix, this is a vector. Just the usual Ising definition of a problem, where these would involve pairs of sigma z terms. These would involve single sigma z, or z's, depending how you like to refer to them. And same for these. You'd have some constraint strength here, which is basically how strongly am I enforcing the domain wall constraint. And this is then your problems. In this case, your things that tell you can't color nodes that share an edge different colors if you're doing a coloring problem. So let's look at a very simple example. 3 coloring on a line of 3 nodes. So 3 variables with 3 possible colors. Therefore, my variable sizes are 3, 3, 3. All right, easy enough. No single term penalties. Therefore, penalty terms is all zeros. Length 9. So just length 9 because that's the length of this. Interaction terms is 9 by 9. With 6 terms which take values 1, which are telling me, okay, I have these sort of purple, blue, green. Well, these 2 can't both be purple. These 2 can't both be blue. These 2 can't both be green. These 2 can't both be purple. These 2 can't both be blue. These 2 can't both be green. 6 constraints. So then these are sort of the indices using the usual Python 0 index thing. And that's it. You give it that, and it will spit out some J's and H's. You see this H core, basically it has 2 variables interacting, or 2 qubits interacting for each of these, and then they don't interact outside of those. These are just the constraints for the ins, and then you have the problem definition. These variables on the in just come from how you build the interactions when you go for them. You end up having to sort of interact with some of these virtual ones. They just basically penalize having a domain wall at the end in the right way. I'm not going to go through the detail of exactly why the structure looks the way it does, but the program does that for you. You can verify, again, I'm not going to do it here. You can verify this does the right thing by hand if you want, or using a computer program if doing it by hand is a bit tedious, which it is a bit tedious. But then you end up with this Hamiltonian, which is just this, hprob, hcore. These s's are my Ising variables. I guess I could have called them sigma z, or I could have called them z, but just called them s for spin. I don't know why. So then you end up with this. And then this kappa is the strength of your constraint. And then you can just sum this all together. And you sum this all together. And this is your problem Hamiltonian for whatever you want, for this simple example, for instance. I'm not going to go into too much detail on that. You can feel free to sort of download that and play with it if you want. I am going to discuss some different bits of future work that relate to this. So one thing I'm going to discuss here is a possible application of this, which is quantum simulation. So the idea here is you treat each variable in the discrete quadratic model as a point in space. These quadratic couplings can emulate many kinds of differential equations. If you discretize them, you just find out that many of them you can express in terms of quadratic bits of equation. That's great. This may also be useful for solving other differential equations, so I'm not going to talk about that here. And if you're thinking of a transverse field Ising model, which is what these devices have, D-Wave devices in particular, basically the transverse field flips your bits, the Ising interactions define your problem or your thing you're simulating. This basically causes the field to fluctuate to nearby values. So this isn't the main focus of the talk, but is worth pointing out. I'm working with Steve Abel and Mike Banowski in Durham IPPP, Institute for Particle Physics Phenomenology. There's some papers on that. This one is just them because we worked on this paper together figuring this out, and then they got really excited and went off and did some stuff on their own with it, which was really cool. Let's think about some more outlooks. This is from the QST paper. And basically here you have driver Hamiltonians, which preserve the valid subspace out of two variable terms. And these are constructed by, so basically the idea here is if you have spin flip terms on this domain wall chain, if they operate on a spin next to a domain wall, that's great. You just move the domain wall. If they operate somewhere where there's no domain wall, you create a domain wall, anti-domain wall pair, and that's bad. You've broken the encoding. So you can actually make drivers that preserve the valid subspace by putting these extra Pauli Z terms on. And what these do is basically by putting a minus sign in front of one, you can say if these two are different, then I do a flip with strength 2. If these two are the same, though, these x's on spin I will cancel. And I actually can only do spin flips that move my domain wall, not ones that create domain wall, anti-domain wall pairs. Hooray. This could also be useful for QAOA or other gate model algorithms, or if you were imagining a bit in the future where you can actually have annealers with what are called multi-body drivers, annealers that involve not just single bit flipping, but multi-bit sort of terms. This is probably longer term in the future. I'm also just going to mention that you get this nice layered structure that I talked about before. And many of these are important problem types. So you may actually want to design specialized ASIC if it's superconducting devices where you actually allow these domain wall chains to be stronger than everything else. This could be important for designing future annealers. Now it's probably worth giving a quick summary. So the first thing is this encoding seems to have given better performance in our experiments, and we haven't seen any downside yet. It had pretty substantial gains. I should mention here my two collaborators from this paper. I realized I hadn't actually put their names on the slides, which is bad of me. This was the first author on this is Jia Chen, my very excellent postdoc, and this was also done in collaboration with Tobias Stolenwerk at DLR. You should try this if you're doing annealing or even things like QAOA involving discrete variables and optimization. You don't have to code it from scratch. There's some nice Python code you can get, which is great. And working with Tobias, this domain wall encoding is going to be included in DLR. So DLR is the German Aerospace Organization. Their next software package they're releasing, they're going to include this. So it would also be interesting to test this on QAOA, which is a gate model algorithm, which is sort of an analog of quantum annealing. I'm not going to claim that the better performance on quantum annealing necessarily means it would do better on QAOA. The constraints you have there are different. The things that are easy or hard there are different. So it's not necessarily clear to me, but I think it would be interesting as a try. And we've gotten some nice early results on quantum simulation. I didn't talk about those a huge amount, but they're early results. We, I think, still need a more rigorous understanding, because the idea I've had of, okay, yeah, you just introduce something that looks kind of like quantum fluctuations is not as rigorous as it could be, but I think there's actually a whole lot of potential here. It's just in its early days. So far there are actually some fairly impressive results, but not quite. Still more needs to be done. So with that, I think I see we haven't gotten questions yet. Hopefully that wasn't too fast. I think I will open it up to questions if anyone has them, though.
Yeah. No, I think it was great. I guess, as you were saying, a lot of the stuff, they are harder to see theoretically as opposed to like playing with the code and these things to actually see. We have a question on the chat, actually.
Yep. Could specialized architectures of qubit interactions benefit the DW performance? So I'm not sure in this case whether DW is domain wall or D-Wave. I'm going to assume domain wall. Yes, I think, that's what I thought. Just didn't want to assume. Yes, I think it could. I think in particular, you tend to end up with very, very particular structures here. You tend to end up with sort of similar-ish structures a lot of the time. You end up with this layered structure in particular if you have quite a few different options. So what you could do is you could say, well, the overhead for embedding actually seems to affect performance quite a lot when you run experiments on these annealers. What if you say, well, okay, I'm going to make a more connected annealer, but not fully connected, and I'm going to make it look like a problem. So let's say a scheduling problem. And you say, you know what, I want to design a specialized hardware, let's say an ASIC, an application-specific integrated circuit superconducting thing, and I'm going to have a bunch of these parallel chains that maybe I don't allow them to be anti-ferromagnetic because I know I'm always going to be using them as these domain wall things, and I engineer them so they can be really strong so that I know that this constraint's not likely to be violated. And then I'll have interactions that are fairly local in time because I know this sort of duration of my events isn't going to be too long, and they're only really going to talk to ones at similar times. That's a much less daunting task than engineering a fully connected graph, which is kind of awful, but still could be really useful. You can still get out of at least some of the embedding overheads there, and could make a difference. So yeah, this is something that I think people should actually start thinking about now, particularly for sort of circuit-based annealers, is what hardware structure do you actually want for specific applications in the real world? And maybe you should be matching those two. Maybe it's worth doing because, yeah, fully connected is, at least for the circuit-based ones, probably not very realistic, and probably not either in sort of the atomic implementations, if we're being honest about it. But having control over what can interact with what, you definitely do, and you can hopefully do better than what's the current connectivity. Even on the more connected D-Wave device, I think there's still a long way to go. And this minor embedding approach, mathematically it works. In principle, it works at arbitrarily any size, but if you're really trying to squeeze performance out, you probably are going to want to a bit match your hardware to your problem. We're probably not quite there yet, but we're probably at the point where it's at least worth thinking a little bit about that. So yeah, great question.
So I had a question. So what kind of quantum field theories are you working with?
So my collaborators were the field theory experts on this, but we were looking at pretty simple ones. So we were looking at basically just simple sort of one, sort of, which is one sort of type of field, and looking at sort of different boundary conditions you can have on it. What you can do is you can do most kinds of at least simple field theories this way. So what's easy to do is local interactions. So if you wanted to do, say, a phi to the fourth theory or something,
yeah,
that would be relatively simple, straightforward to do this way, because that would just correspond to these local penalties that you have on these domain wall chains. And since the derivative is only a second derivative, that turns out that it maps to a quadratic interaction. So it maps to a discrete quadratic model. But yeah, you could do more complicated ones with maybe different kinds of fields and they interact, but we haven't
right. Okay. Thank you.
Maybe that's something you can try, Soham.
Yeah. Absolutely. I think there's all kinds of cool stuff to try with the simulation side of this.
Right. Yeah. That's very true.
And in principle, I think there's a lot of room for trying different things. I mean, you do have, there's a bit of limitation with the actual devices themselves and with what can interact with what and the limited connectivity. But in particular, what you can do is sort of a zero-dimensional one, which is basically just Schrodinger equation, to sort of do a proof of principle and then move up, or argue you could move up. I think in the paper we looked at, we just really looked at the sort of classical mappings. But if you're doing the actual thing, including fluctuations, I think the most they did was 2 interacting points, so barely a field theory. But it's proof of concept.
Yeah. Nice.
No.
Okay. Is there any other question? For those of you, I think those who haven't downloaded the stuff, I believe, Nick, you have other problems within the data sets and the code. It's not just the coloring problem. There's the other one to do with, is it flight gates or something? Maybe you can...
The flight gate one is Tobias's work. And yeah, I have some of the data on that's there, but since it's not really my data, it's just one we took from a different project. It's probably not particularly informative to look at it. You can if you want, and I guess you can use it for something if you want, but it's probably the other one though, the first paper, because both papers have a data repository. So the one I mentioned here is actually the data repository of the first paper. That also has a thing for making artificial scheduling problems. Because basically what I've done for both these papers is, in addition to the first one having this sort of easy domain wall making utility, it also includes all the code and data from the paper, just because that's sort of a good way to make the work accessible and reproducible and keeps you honest, right? You say the data says this, and if you really are confident that they've done it right, then you should be able to put your money where your mouth is, and someone should be able to
That's why.
Yes, it actually does what you say it does, rather than going, oh no, I have this data, I'm not going to show you that, I'll just show you the plot I made. No, so
I know that even some controversies about like releasing or cherry picking the data points and these things. It's
I mean, it doesn't make sense for every project, but in general, where it does make sense, I'm a pretty big fan of sort of open code and open data, and especially in this case, because there's so much potential for reusing at least the code for making this encoding. At least putting something basic on there so people don't have to think about how to code this up themselves.
This I'm a big fan of paper with code, especially the time, because I think this is what academics, especially when you have something new to share, if you want more people to look at it, you want to make it easy for people to get started, and not necessarily having to dive deep into the paper to try to rebuild your stuff from scratch. So it makes it less friction for your work to be tested out there, maybe with the different use cases that you didn't have time to do, or maybe even didn't think about. So
the other sneaky thing for people who are just starting out is it also has all the code for making the plots in the paper. So if you like the way I made some plot, you can, I haven't really commented that code that much, but you can look at the sort of Jupyter notebook that actually made it and go, oh, that's how you get that plot to do that thing. That's how you got that color gradient or that other thing. Which, maybe that doesn't matter for people who are more established and already make a lot of paper plots, but for people just starting out, it can be useful that way too. You have worked examples of like, oh yeah, there's a plot in the paper that I thought, well, hopefully people like the plots. I guess if they don't, they go, well, there's something I never do, but I guess I know how to do it now. But if someone likes it, they can go, oh yeah, there's how you actually do it. But there's how you code it up. Okay.
So So, Ham, you have any other question or something? Because I have an idea, which is to fire at some questions at Nick randomly to see on
Well,
the chat.
I
I'll pick some.
had a
Yeah.
very simple question. I think you might have mentioned that, but I missed it. So why is this called the domain wall?
So that's from sort of just how this idea is inspired is these this break in the chain where you go between 0 and 1 is often referred to as a domain wall. It's sort of a simple domain wall. It's a domain wall in one dimension, basically. So it's not like when you have a solid material and you have a domain wall running through in 3D. It's like just have this little chain and you can go to different ones. So yeah, the important fact about how this works, though, is that it really is a topological defect in the sense that it only exists because of a boundary condition, right? If I have a ferromagnetic Ising chain and I haven't put this funny boundary condition on there, then the ground is just everything agrees. It's only because I've done this topological thing that then I've created this, well, basically topological defect, which turns out is a good way to store information because it's stable. The way I've defined this, there's no actual way to have 0 domain walls, even if you violate the constraint. You always have one. You can have more than one, but you always have to have an odd number, basically, the way it's set up. Because the way I've defined the boundaries, they frustrate each other. And so you have to have at least one place where you disagree. It just doesn't make mathematical sense to not have that.
Right. Thank you.
No problem.
Cool. So
So
I don't see any. Shall we fire some questions to Nick? Anybody wants to start on the thing on the chat? I will pick them randomly.
Great way to spend the Friday evening.
So Nick, which one was your the most influential paper of your career?
Most influential paper of my career, I would have to say, is one called Modernizing Quantum Annealing, which is a single author paper that sort of has a lot of the ideas of this sort of reverse annealing trick before it was really done. So it was basically, here's something you could do with a D-Wave type device. So basically, I'd done my postdoc at UCL, or my first postdoc at UCL, and there, a lot of what I'd done was run experiments on these devices. And so I'd gotten a fairly sort of good theoretical understanding of how they work. And so then this was, well, I know what some of the capabilities are from reading some of the experimental papers. Here's a way you could use these as a computational tool. It was actually sort of interesting with that. So I thought, okay, there's this idea. I'd sort of talked to people. No one really seemed to have had the same idea. I think maybe actually some people had, but not publicly. But so I would say, how do I get anyone interested in this? Went to AQC 2016, said, okay, how do I get people interested in this idea of hybrid algorithms? The first talk was Google talking about why they think quantum annealing might succeed. And they talk about a very similar kind of hybrid algorithm. And it goes, well, okay, getting people interested in this isn't going to be the problem anymore. Making sure that people, are interested in the sort of way that I'm interested in doing this is then what it's about. And then it did, and here we are. But I'd say in my case, one thing that made a huge difference there was having a very supportive supervisor who let me go off and write a single author paper on something that wasn't exactly the thing that my postdoc was on. And that
That's interesting
I
because
would
we
say
have
it was very, very helpful for my career, and it ended up making.
Do you think this? The thing. Maybe this is something, Soham. If you want to comment, also, don't worry. This thing will not be heard by anybody at your institution. From the outside, obviously, I'm no longer in academia. I'm not in academia. These things, but I sense, since you mentioned this thing with your supervisor, who gave you space and time, which is what I'm assuming he did in order for you to pursue the thing. But it seems to me nowadays, like graduates, PhDs and these things, they get so much under pressure to like publish and perish type of stuff that maybe it's like it's putting I don't know. Will that be like from your point of view? I just want to take your pick your brain on this. Do you feel that the downside of it, potentially, in terms of people taking riskier ideas, to try to, make breakthroughs or, create new opportunity for research?
Well, so yeah, I think, I think focusing on just quantity of papers is probably, I would say, not the right approach, not what I would recommend. Trying to do things that are a bit innovative and things that are kind of uniquely yours, I think is actually probably what's really important, coming up with something sort of a bit different. Maybe someone who is more, inside of one of these inside of one of these sort of bigger groups, maybe they're contributing to something like that might be an important step. But I think getting a fair number of papers is of course important, but also having good work and really sort of almost establishing your sort of identity as a researcher, let's say. So people know sort of the kind of things you do when you have your own sort of niche that's really your thing. And ideally is also separate from what your bigger group does, if possible, so that it's not just, oh, that's a really good group and it has such and such postdocs working there, but I don't know what any of them do. Instead, it's this person does this, and that's their stuff, and it relates to their group stuff, but their specific stuff is this one thing, and having that, I think, is what can be valuable on sort of moving to the next stage.
Yeah, so good advice to all the principal investigators on the audience, huh?
Yeah.
Does anyone have any other question for Nick on the chat? Okay, I will ask another one. I know your time is. What's your favorite book outside physics, outside your outside science? Let's say
outside science.
I know you are interested in politics and other stuff.
Yeah. That's a tough one. Yeah, that's a really tough one. I don't know. I know some people say it's boring, but I actually quite like Catch-22.
Okay, there is another question that just showed up on the chat. I don't know if you want to address it. By the way, if you have to go, you let me know.
No, I'm fine. So the question is, could quantum transport problem be modeled with domain wall encoding? I think that kind of depends on what kind of problem. This isn't a kind of problem I'm particularly an expert in, actually. In general, what it's good for is anything where you have sort of discrete variables that can only take a single value. So these could be like points in space in a field theory. For transport problems where you have a limited, let's say, conserved quantity of something, It's harder to see how the obvious way to include this, but maybe there would be. So I don't. I'm not immediately seeing a specific way to do it, but I'm not going to say no, it can't be done. Do you have anything specifically you're thinking of, or just sort of generally asking about it? Because if you have something specific, maybe I can comment on it, or maybe it's something I don't know enough about myself. Okay, I'm not seeing anything, so I think it may have just been the more general question. So yeah, I can't see an obvious way to do that, but that doesn't mean there isn't one. No.
But I guess as you put it, there are so many directions that can be explored with this thing. So yeah, okay, so I don't see any other questions, and I don't want to take much of your time, and Nick and the rest. So yeah, thank you so much. It's been great. I look forward to checking out the stuff, and I'm sure the guys, everyone in the audience, will be looking at the code and playing around with it, and maybe come up with other ideas. And we look forward to having you back again. Huh? Maybe on the domain wall.
Absolutely, I'm happy coming back, and I mean, I guess I'll have to go get some more results. But yeah, I like doing these. I'm certainly happy to come back and give another one. We should probably also at some point chat offline on sort of working on stuff together. But that can take place offline. But yeah, thanks again for having me. And yeah, I like giving these and would be happy to maybe just when I start getting results that seem like they'd be good for some of these, maybe I'll start contacting you and going, hey, would you mind? Yeah.
You're always welcome, Nick. Thank you so much for taking your time and sharing this with us. And to the audience, thank you so much. This will be available on YouTube later if you want to, go back again and rewatch the talk, especially after you download the materials, the code, and the data. It might be good to come back and refresh. And Nick, I think these slides will be available on your website, right? On the thing. So
I will put them up. Yeah, I'll put them up.
Yeah.
I mean,
I will email.
Yeah.
I will email people on the link to where the slides are in case they want to look at it. If you don't mind, of course.
No. I don't mind. I'll probably slightly edit them to add Gian Tobias's name in there because I realized as I was giving it I don't mention the two collaborators I did this with. That's probably bad. All right.
I think names are
but other than that, it'll be exactly what I gave here.
Okay. Okay. So thank you so much, everyone, and have a good weekend, and see you next time in our next webinar. Thank you, Nick.
See you.
Thank you, everyone. See you.
Bye.